Yeah, good evening. So, welcome to this last live session of this course, and this is week 13. So, uh, for those who haven't seen the week 12, so in last week I have taken two live sessions, one on Tuesday, and that is the normal usual live sessions which I normally take, and another one was on this Friday. It was from 4 to 6. I know like it was the last moment decision to take that live session. That's why I think nobody was there. So if those who will be listening to this YouTube live session, then they can rewatch that week 12's second live session that was on Friday. So I have posted that on my YouTube channel, so you can see that. So yeah, so this will be this week 13, the last live session for this course, electrical measurement and electronic instruments. So I today I only have like some of the assignment questions which you have already done, but I found those questions to be good, so that's why I will be doing that again. But apart from that, if you have any doubts or something, so you can like write in the chat box, or yeah, have even I think the discussion forum will be that will remain open for like till the exam date or something, so we will be replying there also, so no issues. So meanwhile, if you get any doubts, so this will be a very like I won't say there will be any new questions for you, but this is so I will be here. So if you have any doubts, or if other students also join, then if they ask something, then we will be solving that. Otherwise, yeah, this will be that will be all for this session. So but yeah, so but I will be solving with some of the questions which I found to be good, and they may be useful for your like based on your exam point of view. So we will revise them and how to solve them and all, so we'll be seeing and we'll be looking into that. So yeah, so let's start with the first question. That is like so in the initial lectures you have been taught. So first we'll recall like what we have been taught throughout this course. So first we just let me open it. Yeah. So in starting of the lecture, we came across these PMMC instruments, like how they are made, what is the purpose of oil, soft iron core in that. Then we had this permanent magnet, in which between that there was some coil. So this is just like revision I'm going through. The pages and so yeah. Wait, I will tell you. Hmm. So yeah, we talked about PMMC meters, like how they are made and those their construction and their this deflection formula, torque deflection formula, like that is k theta when deflection torque becomes equal to controlling torque, then it is like we denote this by this formula, and we have this magnetic flux density b. I is the current flowing through that coil, and n number of turns of that coil, and a is the cross sectional area. So then we talked about, so we also talked about that this only measures this average of that whatever the input signal is, so it measures that. Then we talked about some this electrodynamic instruments, electrodynamic instruments, how to like so instead of permanent magnets, now we had this electrodynamic magnets where we feel so we will like give some fixed current, and if you are measuring like unknown current, then it will deflect and the torque will be directly proportional to the fixed coil current and the moving coil in the and the coil current. So it will be directionally proportional to both product of these two currents. And then we talked about this the this if we remove this proportionality constant, then we will have if im dm by d theta. So this is the mutual coupling m between the coil and the fixed coils. So this mutual inductance between fixed and moving coils. And then we had this then we saw different configurations of this, and then we compared PMMC with electrodynamometer, like so direction of the deflection torque or theta depends on the direction of the current in PMMC. And for AC, like alternating current, like pointer oscillates, it will keep on oscillating. But in electrodynamic meter, we had the like the TD do not depend on the direction of I, because it will become this quantity if the current coil, fixed coil current, and the moving coil current have the same current passing through that, then this will become I square, so it will not depend on the direction of this. And this can electrodynamic meter can measure both AC and DC. Then we talk about the like dial positions. If this in PMMC the scale is uniform, in this the scale is uniform. In electrodynamic instrument, we don't have that uniform scale, and it indicates RMS value, whether while this PMC meter indicates average value. So these were all basic comparison between this PMMC and electrodynamic instruments. Then we talk about moving iron instruments and how we can like move an iron bar with the help of like magnetic field, which is like where the wires are being coiled on a core, and the current flows through that, and there is an iron core or iron material which deflects based on the magnetic fields produced by that current which is being flown in that coil. That is for MI meters, moving iron meters. So that, as the name also suggests, so here the deflection torque was equals to again I square into half dl by d theta. So here there is no mutual inductance, but here is self inductance of the coil, and this also like measures RMS and AC, RMS of that AC. And in this case also scale is not linear, because here also non-linear scale, non-linear scale, here also non-linear scale. Okay. So this was about moving iron. Then we talked about electrostatic instruments. That is based on the capacitive principle uh, of two discs basically. So the charge accumulated on each of the disc. Then based on that we calculate how much deflection of torque is happening, how much torque deflection is happening. So for that it was like electrostatic. If we talk about electrostatic instruments, So it was like TD equals to half dc by d theta v square. So this was directly proportional to the voltage of the signal applied. So this was moving iron. Then we talked about some dynamics of like equations of moving system, how this differential equations of this damping torque, damping torque, controlling torque, and deflection torque, how the differential equation looks like, and how we can relate it to the resistance of the coil, and when this overdamping, critical damping, and under damping conditions happen. So that also we discussed. So this was about. Then we talk about ballistic galvanometer. Then later on um, in the lectures, we talk about ammeters, how to increase their ranges, voltmeters, how to increase their ranges, then how to apply different switch conditions in these ammeters and voltmeters, and correspondingly how to change their ranges and all. Then we talked about rectifier based voltmeters and ammeter, as we know that PMMC. So if we have this PMMC meter, so basically it is an application of PMMC meter. If we use PMC meter with the help in series with a diode, then we can rectify the output signal, and it can be a half wave rectifier. And also if we have this if we have configuration of four diodes, how things will be like, so something like this. So if PMC meter is here in between, so how this will be giving a full wave rectified signal. So this also we saw. So this was about the diodes in PMC meter. Then we talked about resistance measurement, how to measure like low resistances, then high resistances, and all those things. Then we talk about four terminal resistance and why it is useful. And we also measured like high resistance, using their surface resistivity and volume resistivity and parameters. We talk about that also. Then we talk about various bridges. But before bridges, we talked also about this one. Uh, Wait, just. So then we talked about watt meters. So I think this will be very important for your. This will be important for the exam. So one question may come from this watt meter, as we talk about the different connections of power coil and current coil, and we know, and in my live sessions also I have told you about like to keep this in mind, that voltage of power coil and current of current coil, and the angle between these two coils PC and CC, the cos of the angle between PC and current coil. If you know this concept, this basic concept, then you can solve any type of configuration for any type of wattmeter. So we have done a lot of wattmeter questions also, three phase questions, like three-phase wattmeter questions. Some derivations were there, but I think in live sessions, whatever derivations I have told you, that are not that important, because that was just because based just for your understanding and more depth learning. But you should be focusing more on this, like how the questions, based on only on the lecture topics, and some of the extra questions which I gave you in live sessions. So that will be enough. Don't look deeper into these derivations which I told you. So anyway, but this power of a wattmeter is like the product of the voltage across the power coil and the current through this current coil, and the angle between these two, power coil and the current coil. So this was so if you know this, then you can solve any configuration of wattmeter. So we saw different configurations of wattmeter, and after that we saw bridges. Like there were lots of bridges, like different types of bridges. We saw V-stone bridges, like basic concept of V-stone bridges we applied to many AC bridges, like to measure different type of capacitances, low value of capacitances, medium value of capacitance, and even high value of capacitances. Same for inductors. We saw different bridges, like Maxwell inductance bridge, I think, if this has been taught to you. Otherwise, we also talked about this, how to reduce the lead resistance of any measure of particular measurement using bridges. So that was like this was Kelvin doubles bridge. So in on that we saw some questions also. So that was also like Yeah, that was also good. And then we talked about this. Yeah, bridges. Then yeah, in bridges, there that the important thing is like to remember that quality factor concept, quality factor, that is Q, and dissipation factor. So in one of the live sessions, I also told you about this thing. So I have also told you about this. Like I have given you a table in these live sessions. Like what are the quality factors for each and every configuration? Like if it is like series RC or parallel RC or series inductor or parallel inductor. So I have given that table to you, so you can go back and see that video lecture on this. So dissipation factor is basically Q equals to 1 by D normally. So if you know this quality factor and you know on which coil you have to apply that in that bridge, then you can solve this. So bridges, I think bridges questions related to bridges will be quite easy. Just keep in mind to apply that Wheatstone bridge concept very carefully. You can relate the magnitudes of the bridges, of the bridge arms on, and also you can relate the, I will say, the angles of these arms. So relating both of them, so you can get to your desired results. One more thing to keep in mind, what I feel like, whenever you are having this this magnitude base, like this relation, the like let's say there is something like this. Let's say this one z1 z2 z3, I would say z4. Okay, so across this we have to measure a and b. So the normal uh, balance based condition will be z1 by z3 equals to z2 by z4. So the point which I want to tell you here is that it depends on the equation, like whether you have to solve straight away from this only, or you have to rearrange the element. So either you can bring z4 like above, at the numerator of the LHS, or you can bring z3 at the numerator of this RHS of this equation. But it depends on the equation which have been so ultimately you have to relate the real and imaginary part of this equation. So if you will not do this correctly, you might find things to be like complex. So because then even if you are relating some real and imaginary things and they are complex, like they are difficult to solve, then you will be in difficult situation. So just to keep that in mind, try to first look, okay, can we rearrange this equation, and if we are rearranging, will the equation will become easier to solve or not, like will we be able to equate the real and imaginary parts both of these on both sides, and can we get to their desired results. So that's requires some of practices for this bridge questions. So in live sessions also I have given some of the questions, and you can see them in these assignment questions also. So you have plenty of questions to practice, so just keep that thing in mind. So after bridge, in this, then we talked about the single phase energy meters, and like how that this rotates and how it is being measured. But nowadays that is not being used because people used to steal energy, electricity and all, by placing a magnet on that. So that's why they will slow the disk rotation. So they were trying to steal the electricity, but now we only use digital meter. But it was important to tell you about the concept of that energy meter, so that you should know the fundamentals of that. And then what we learned, yeah, so polar potentiometers and phase shifters. So for this, like if you will get any questions from polar potentiometer and phase shifter or coordinate potentiometer, so then those questions will be I will say based on the lectures only. Okay, so try to just remember what was being taught in the lecture, on the course lecture, and you should know like the basic structure of that coordinate potentiometer and this polar potentiometer and phase shifter. So that is maybe a one numerical based question can come from that. But if you are not knowing the working of that, you won't be able to do that. Okay, so then we talked about CT, current transformers and potential transformers, and how they were used, and that condition for uh, like this potential transformers. So in potential transformers, we drop this voltage. So V2 is less than V1 is high. That means I2 is higher. So I2 means high, I1 is less. Okay. So this is one thing. And in current transformer, it is the other way around. The I1, the primary side current is less. Oh, sorry, it is high, and the secondary side current is high. So just like keep this thing in mind. Like so, if this is high, so you can tell like N1 by N2 is V1 by V2. So based on that, you can comment on the number of turns, and remember that short circuit conditions in potential transformer and current transformer. What will happen if we short or if we open the the prime this the secondary side of this, either the potential transformer or the current transformer. That is important. And then we learned about this. Then we talked about different latches, SR like flip flops, SR flip flops, and JK. I think JK you have not been told. So SR flip flops you were talked about. So you were told about SR, then D flip flops, then T flip flops, and we solved some of the questions on that also. And yeah, you can expect one question from this flip flops one. uh, but yeah, you can expect that. But I think digital part, maybe easy for you. uh, that will not bother you enough much. Okay. So then yeah, so then we talked about, then we introduced this operational amplifiers. So I think that will be also an important topic for your exams, because from operational amplifiers, one like questions will be can be from like negative feedback, the basic of operational amplifier questions. Then some questions can be from Smith trigger, or like getting the upper threshold and lower threshold values of those Smith triggers. Then you can get questions from that also. So like operation amplifiers are important. Like just go through that. Then we talked about emitter formula or BJTs inside the operational amplifier feedback. So those questions also have like I have given you in the live session. So I have like we have practiced some of those questions also, which were having this emitter BJT in like basic BJT or diodes type of like questions in their like diode types of like elements in their feedback and how to solve them. So those things. So in operation amplifiers, basically just first thing to look for is like what feedback, either is that a comparator, or if a feedback is there, whether that is a like a negative feedback or a positive feedback system. So if it is a negative feedback system, then no need to worry, you can solve with that virtual short concept, and you can use KCL, KVL, whatever in that negative feedback. But if it is a comparator, then simple thing you have to keep in mind that the non-inverting terminal voltage, if it is higher than the inverting terminal voltage of that op amp, then you will get positive saturation and vice versa. Okay, this is the concept of comparator. And in case of positive feedback, the same concept applies, that it acts as a comparator, but the only thing is that we have this upper threshold and lower threshold limits for positive feedback system. So instead, like so the only the thresholds changes for that, and you should know how to calculate that the threshold limits, and then hysteresis band of those operational amplifiers. That will be important if a question comes from that. So yeah, then we talk about this analog to digital converters and digital to analog converters and different types of them. So in that resolution, like concept of resolution, and then in this dual slope conversion of like analog to digital, then the so that those equations like the input, the integration time and the deintegration time of that dual slope converter. So that equation you should keep in mind. And then I also told you about like type of ADCs. I gave you a table like in which we had this type of ADCs and number of clocks were there and how much time each and every ADC is taking. So you can see those previous live sessions. I think that was of week 9 live session. So you can go through and check those two. So if you will be remembering that table, then it will be easy to like solve some of the single correct questions which talks about like which ADC will be faster, like that. So that will like save your time if you remember those tables. Yeah, one more table I just remember I gave you that for different signals, like for like different signals, what are their this average values and their RMS values. So that is very important table. I think that was in my live session week 4, or I think week 3. I think week 2 or maybe, but I don't remember. But just go through that table. That is very important. Like those average and RMS values of whatever waveform you are getting, you should know, like it should be on the tips, so that you should not be getting confused while solving those things in exam. Although you can solve that like numerically using the basic formulas of average and RMS, that mathematical formulas, but it is good if you remember these uh, these values of average and RMS for different types of inputs like sinusoidal, triangular, seesaw, and all those inputs, and yeah, square wave also. Okay, so that table was very important. Then what we were talking. So yeah, operational amplifiers, then instrumentational amplifiers also we used. We saw in these lectures, and why they were used. What was the need for that? We talked about that in the lectures. And then yeah, so then in the one of the last sessions, like week 11 and week 12. Week 11 we talked about this function generator and oscillator circuits. And you should remember what is the structure of this IC 555 timer. That will be important. And this function generator, the basic function generator structure which you have been told. So how these limits are being changed, the upper threshold and lower threshold. So all are these basically positive feedback applications of operational amplifiers. So if you know how to calculate that upper threshold and lower threshold, you can easily get these the concepts of function generator, oscillator circuits, IC 555 timers, and yeah, so these things. And stable oscillator also, monostable oscillator also. So all these things you can get. Then then we talked about these oscillators, so like there were different phase difference. And then we talk about like what if like x and y signals are there, then if there's some phase difference, then how will be the Lissajous pattern on that oscilloscope. I have corrected that table, I think in week 12 or week 11 session. So first, initially I gave you the wrong table, but I just corrected in the next live session. So keep that thing also in mind. So just if in your notes, if you have noted down the wrong table, then just correct that. And then we talked about these Lissajous patterns and how we can calculate the frequency of a Y signal or X signal based on these horizontal and vertical tangents and this intersection points. That was one thing. Yeah. In the last week also, in the lectures, it was being told this emitter follower configuration, and how it is used, and how it is used in linear ohm meters and all those. And we solved some questions also. Some assignment questions are also there based on this. So that was also there. So this was all about this course. And yeah, we learned lot many things in this course. I hope you people learned a lot of things. So in this we'll shortly we'll go through the some of the questions which I found good. And yeah, so let's see. So how we'll solve them, so it will be a good revision for you. So the questions are not like they are just 8 or 9 questions. I think 8 questions, but these are like based on your assignment. So you have already done that, but somehow I feel like these were wrong. Some answers of these were wrong when you get the answers or solutions. Then you can see this, like what was the concept. And so first, like as I talked about PMC instruments, this will be important. So 200. So this question talks about like there is they have given this 200 turns of this moving coil PMC instrument, and they have this length width of the coil also. They have given 1.5 centimeter. The air gap flux density is zero point 0.9 Weber per meter square, and spring constant is also being given. The resistance of the coil is 100 ohms. The coil is wound on a backlight former, that is an insulator. So the first question, they say that estimate the deflecting torque. So all the deflecting torque equations are very important for you. So like for this it is the deflection torque is this. If we for PMC meter, so flux density we know. And just also one thing to keep in mind that just keep in mind this units. So as in this question you will see, so this sorry, so this is air gap flux density is point 0.9. Just so this is point 0.9. So the unit is Weber per meter square, that is SI unit, no need to worry. So then I we have 4 milliampere, 4 milli into N is 200, area is 1.5, length into breadth 1.5, but the unit here of this is centimeters, so it will be 10 to the minus 2. So for one, for 1 10 to the power minus 1 for this length, and another one for 1.5, that's why minus 2 is there. Okay, so this is there. And yeah, so by solving this we will get uh, this as 162 micro nanometer. So see, they have asked you in this micro nanometer SI unit, so just keep that in mind. So whichever unit they have been asked, so you have to give the answer in that unit. So this was easy. Then the next question, estimate the sensitivity of the meter. So sensitivity they have given this also, but it can be, so if you just remember the this formula, so it will be like VNA divided by K. Okay, so or it can be like in another words, K theta is what? K theta is T deflection torque. So you know this deflection torque, and yeah, K you know, it is being given in this question, K. So theta is what? T TD by K. So for this is for 4 milliamperes of current. So if you know theta, so theta per milliampere, so this will be for 4 milliampere. So for 1 milliampere, that is per milliampere, it will be theta by 4 milli. So this is also equal to sensitivity. So basically, the for 1 milliampere, how much degree of change is being observed is the sensitivity of that meter. So either if you know this formula correct directly, you can apply this. Otherwise, if you, this is the basic deflection torque equation, K theta equals to deflection torque, and you have just calculated the deflection torque, and then based on that you can solve theta. And this was for 4 milliamperes. For 1 milliampere, you can just divide that by 4 milliamperes, you will get the sensitivity sensitivity. Yeah, okay. So this is also there. So then the next question, the pointer says stays at 0 degree when no current is passed, and the pointer can move up to 90 degree. So they are saying that it was at 0 degree if no current is there, and it will go for 90 degree if, like, it is at full scale deflection. So this is this instrument looks like this. Okay, so for this, like, they are asking at max estimate the full scale deflection current. So the full scale deflection current they are telling us to calculate. So for this, we know that for 1 milliampere, so basically the sensitivity for this, if we calculate either by this formula or this formula, we will get it to be as uh, 23.14 degree per milliampere. Okay. Now using this, let's say, so for 1 milliampere we are getting 23.14 degree of deflection. So this, by this we can easily calculate for 90 degree how much deflection we will getting. So by unitary method, simply into 90, we will get the current basically, and this current is equals to 3.88 milliampere. So for 23.14 degree, we were getting 1 milliampere. For 1 milliampere, we were getting 23.14 degree of deflection. Then, then for 90 degree of deflection, that is the full scale deflection, we got 3.88 milliampere of deflection or of current. Okay, so this was the full scale deflection current. So these kind of questions, I think these are easy, but still. Then we have this estimate then that typical increasing range of ammeter or voltmeter questions are there. So one question is like Estimate the required shunt resistance to convert this PMC instrument into an ammeter of range 0 to 100 milliampere. So just you have to keep this thing in mind that PMC meter, and we have a resistance of its own. Like this meter is having its own resistance, that is 100 ohms. And if you are making an ammeter and from a PMC meter, you have to keep in mind that you have to apply a shunt resistance in parallel to this PMC meter. Okay, this thing you have to keep in mind. So using this, so simple, you know that full scale deflection current was 3.88 based on the previous question, this third question. So so this is like from here it is 3.88 milliampere current is going flowing, and they are asking for us to calculate for 100 milliamperes of current. So the rest of the current will be what, 100 minus 3.88 milliamperes from this branch. So you have to simply equate the voltage of this branch and the PMMC branch, and you have to equate them, and you will get the unknown value, that is the shunt resistance. So the shunt resistance for this, it was around 4.03 ohms. But that I think answers, only the concepts need to be revised. So this was for this. So now this is very important. The next question, which might some may face some little bit confusing. Like what will be the response? So will that be underdamped, overdamped, or critically damped? For these kind of things, you know that this equation d square d theta by dt square plus it was k d theta by dt plus uh, just let me check what was the differential equation, so that I don't give you the wrong equation. Just wait. Yeah, so it was uh, okay. So this is T dam. This is T dam d theta by dt, or we can say K dam. This is K dam plus K, that is the spring constant, K theta equals to 0. Okay, so this was the equation which you have been told. So based on this equation, we derive we derive that this condition for this all critical damp and all those things. So B square equals to 4AC if this is the condition. So B was basically this was BAN square divided by RC, the coil resistance plus the external resistance which has been added to that. Okay, so this is B. So it can be like so this is like the, so if there is a series resistance which has been added to the coil, then this is RC plus RX. Okay, if it is a parallel resistance being added to that coil, then it will be RC parallel RX. Okay, so it will depend. So I think in voltmeter cases this will be the case, in ammeter this will be the case. Okay, so you know this B and A, A and C are like A is the moment of inertia, that is J, equivalent to J, and C is the spring constant K. Okay, but I think moment of inertia you will not be having that information about this J most of the times, but sometimes you may get that information. But anyway, so just you have to keep this in mind. Okay, so you had this B square equals to 4AC condition, and this will become overdamped in case when B square is greater than 4AC, and it will become underdamped when B square is less than 4AC. Okay, so just calculate what will be B normally, BAN square by RC. Okay, so this is B. So in this equation, if you add RX, like if you make that, so this is for PMMC, simple PMMC, you have this equation for B, that is RC, the coil resistance. But if you are making that, let's say emitter, because in this case you have been in this question you have been told to make an emitter. So for emitter, So what is happening? So for emitter, there is a shunt resistance. So this will become RC parallel RSH BAN square. Let's say this is BA. So it is very clear that BA. So this will be definitely less than RC because this is now a parallel configuration. So BA will be what? BA will be greater than B. So if this PMMC instrument initially without increasing its range, it was in critically damped condition, then if we make an emitter out of it, then we are increasing this BA. That what does that mean? That means so B initially it was 4 AC. So now it has increased from that. So B square was equals to 4 AC. So BA square will be greater than 4 AC. That means whenever we you go for emitter, it will become overdamped. Okay. And in another in for case of voltmeters, what will happen? So in case of voltmeters, if so BV will be what? BAN of square divided by RC. Now we are adding a series resistance. So instead of a shunt resistance, we are adding a series resistance in case of voltmeter. That now you all know that like we add series resistance for voltmeter for increasing the range of voltmeter. So this is RC plus RX. So now this will do what? This will make this BV square less than B square equals to 4AC. That means this will be under damped. So whenever there is a voltmeter, it will be under damped case for that voltmeter. And whenever we make an emitter out of a PMC meter, so it will be a over damped situation. Okay. So this will be important for you. So this might since this can be confusing, that's why so yeah, because in next question they are asking to make a voltmeter out of this. So they told there is a PMC meter and this was 100 ohm that coil resistance, and then we added this RS. We don't know about that. So this was 25 volts, which has been increased. Initially, it was some range. So this is 3.88 milliampere. Again, that full scale deflection. So we know this we know this value. We can get 3.88 into 100. We can get this value V1. We know 25 volts, so we can get RS also. So this is basically 3.88 milli into 100 plus 3.88 milli into RS equals to what? 25 volts. So you can get RS from here. But now the next question was like, will this be under dam, over dam, or like max it under dam or over dam? So for this, like as I've told you, like we have added one resistor in series that will make this B value less than the critically damped condition. That means we will get an under damped response in case of voltmeters. Okay. So this was the logic behind this. Yes. Now you can face questions like this, as these are also like so like some questions may be on loading or something like that. You can also so here like there's no load no this discussion of loading in this question, but this is basically a question where we have to find the resistance of each and every ammeter and voltmeter, and also the load resistance, that is Rx. So instead of starting from circuit 1, we'll start from circuit 3, and we know that the voltage dropped here is how much? 200 volts. So it's not necessary that you will get this only, like this kind of structure. You may get something like let's say you have been given the power supply at this point. So you it is being given that the power being supplied from this source is something, some X. So you know that, and then you have some variables, like you have this voltmeter range, like you have this voltmeter value in some part, or you have some this ammeter value, and accordingly using this power supply from the source, you will have to find the current being flown into the circuit here, or the voltage being dropped across this. So it will depend, like it will depend, but the concept is like just start from the circuit which is easy to solve. Like in this case, this was a circuit where we have this 200 volts directly across this voltmeter, and we know the ammeter reading also. So we know that this current will be flowing through this voltmeter also, because these are in series. That's why we can easily get this RV, the voltage, the resistance of this voltmeter easily. which is IA equals to 200 volts. So RV will be 200 divided by the current. So since we get RV from this case, then we can use these conditions. So I'm not solving this, as you have already solved and you have the solution also, but only the approach matters. So this, like, then we had this 3 amperes here. This is 273 volts. Now you know the resistance of this, you can get the current from this, and subtracting with this current you can get current from here also, and you have the voltage, then you can get the Rx. So if you know Rx, Rv, then now you can easily solve this Ra also in this case. Okay, so this was about this. Then these kind of questions, like where there's a input source, a battery is there, then you have a load, and you have been asked like the total resistance of the pressure coil. So now there will be different configurations of this wattmeter. So initially they have asked told that RCC, the current coil of that resistance is having 14 ohms, and power coil having a resistance of 700 ohms. Okay, so you have these two things of a watt for a wattmeter. So now you will see. So initially they asked for like simple, what will be the power supplied from the source and what will the power consume. So power is basically what, VI. So you know this V, and only the I is you. So I you can easily. So this is very basic, easy question. The important thing is like how the wattmeter connections are being done in order to measure the power. So you just have to consider the voltage drop across the power coil, that is VPC. Okay, measure that voltage. Some using your KVL, KCL, whatever knowledge you have of your circuits, use that. Just get the VPC, the power coil voltage. Similarly, use your all basic electrical circuits knowledge. Get the current from the current coil, ICC. Multiply them, and since this is not an AC circuit or like some inductor capacitance is not there, so this will be cause I think 0. So you will get this value. Okay, so there will be no phase difference. Otherwise, you will have to keep in mind the phase difference also for this. So here, like the voltage was this, and current will be after that. So this is one configuration. Okay. Another configuration is like, see, power coil is being now attached across the load, and the current coil is attached towards the source. So the power will change. Okay, because the CC and PCs are having some resistances of their own. So because of that non-idealistic conditions, we will have different values for this estimate the power consumed with this wattmeter. Okay, so again this power coil will have this voltage across this load resistance. Get that and get this ICC. You will get the answer, power consumed for this. So I think you have the solution sheets for this. So I'm not solving this, only like telling you how to approach it. So this another question is there. So this A1, A2, A3 were there, so they have given the readings also. But since just like till now you were being yes, you can switch on your mic and you can ask them.
Sir, good evening, sir.
Yes, good evening, good evening.
Sir, sir, explain power consumed by load
Yes.
in that watt meter. Sir,
Hmm.
power consumed by.
By the load, yes.
Sir, please explain that.
Okay, okay. So yeah, so I'm telling. So okay, I will solve that. Like I'll solve that. So what is happening? So we have RCC. RCC equals to 14 ohms and RPC is 700 ohms. RPC is 700 ohms. This is 14 ohms. So we know this is 14. This is 700 ohms. Just clearing these things. Okay. So we have this. Okay. So this is ICC. Why this is ICC? Because the current coil is being directly connected to the source, this terminal, and this. So this ICC will be flowing through this ICC. So then there will be some load current and some power coil current will be there. We don't know about that. So first solve this. So let me check if we have any more knowledge. Is there? Okay, no other knowledge. So the circuit will look like this. If you just so this is part current coil resistance 14 ohms. This is 700 ohms, and this is 80 ohms. Okay, so just solve this what will be the parallel combination 700 parallel 80. So this will be the equivalent resistance of this part, and then there is a series resistance 14 ohm with this, so this will be 14. So we have a circuit with this total resistance R equivalent, I will say. Okay, and we have this 120 volts here. So if you have this R equivalent of this part of the circuit, then you can get this ICC. So what will be ICC? The voltage 120 divided by the R equivalent. That will be 120 divided by this thing. If I will solve it, just wait, I will use my calculator to solve this. So it is 700 into 80, 700 plus 80 plus 14. So it is 85.79. So this is 85.79 equals to 120 by this. So it will be 1.39. So we have this current 1.39. Hmm. So we have this current, and then this so this we know now. Now our next step is to calculate the voltage drop. So we had to find the estimate the power consumed by the load. So now we have to find, so what is the power consumed by a wattmeter? What does it show? So it is VPC ICC cos theta is zero. Theta is zero basically. So now we got ICC. We only have to find VPC. So ICC is here. So if we just solve this parallel combination, so this was what 85.79. Okay, so this is 700 parallel 80. This is 14. We know this is the current. The current here is 1.39, and this is the input source, the input voltage source. 120 volts, 700 by 80. So just solve this. So we can get the voltage drop across this. So this is VPC. This is what VPC, the voltage across the power coil. Okay. So the current we know, so we can get what is VPC. VPC will be 1.39 into 700 parallel 80. So just solve this thing. So we will get so we also got VPC. Now we have VPC. Now we have ICC. We can get power. Okay. So I think you now you got this, how to calculate this power consumed by the load.
Yes, sir. Thank you, sir.
Okay. Okay. Wait. So sorry. Just a clarification. Just a clarification. So this is basically the wattmeter reading. Wattmeter reading. So VPC we got from here, ICC we got from here. But now to calculate the power from the load, see the load is this one. Okay, I'll add a page here. So now we have to calculate the load resistance. Now see VPC. Now we know this is VPC. We have calculated from here because we knew ICC. Now this is RL. So what will be IL? IL will be VPC, because this voltage drop is same across the load resistance as well as the power coil resistance. Okay, so VPC divided by RL. So this will be our load resistance. So what will be the load power? It will be, you can either go with IL square RL, or you can go with VPC square by RL. So both are same. Okay, so IL also you know, VPC also you know. So either of the equation you can use, they are equal. So either IL square RL or VPC square by RL. So you will get the load power. So this is the load power, and this thing which I told you here. So this is the wattmeter power, wattmeter reading basically. Okay, and that will differ. So you normally use wattmeters in your circuits, and you get to know, okay, this is the power consumed by the circuit, but it is not actually true. Why? Because some of the power is being consumed with this by this power coil and the current coil. So if that is the case, so whatever the load, the power is taken by the load, that will not be equal to the this wattmeter power. So this load power, that is PL equals to, I will say, IL square R, is not equal to the power of wattmeter, that is equals to, this is not equal to VPC ICC. Okay, so this is the, so this was about this. So now, yeah, that was the that was for these different wattmeter connections and all those things. Then we have this. So we had these three types. So another type of question, like we have three types of ammeters, and then the problem with this question is that we don't know this Z, whether that is an inductor in series with R, or only inductor, or capacitor in series with R, or parallel. We don't know anything about this thing. So but we have this ammeter readings here. So A3 is 8.25 amperes, A2 is 3.25 amperes, A1 is 5.75 amperes. Okay, so the resistance here is 700 ohms. This we know. Now they are saying all emitters are ideal. Okay, estimate the magnitude of impedance Z. So you can do like a lot of things. One thing you can do, like uh, so okay, the starting for this is like to calculate the drop across this R. V, I will say V. So that same V will be the drop across this Z. So if we have to calculate V, because we know the branch, this branch A2 branch current, that is 3.25, and we know the resistance of that branch 700, we can get this V. So this is V. Okay, this V is the same voltage drop across this Z. So what will be Z? Z will be the current through that branch. Sorry, V, that is the drop across that branch, V, divided by the current through that branch, that is I1. So it will be 3.25 to 700 divided by what? I1 is 5.7. So you will get Z. So this is the magnitude of this Z. Okay, this is one thing. Now, now the next question: estimate the power consumed by the impedance Z. Now, in order to calculate the power, so you should uh, just wait. Just let me tell you. Yes. So for to calculate this power, so basically the power for a circuit where there is some phase shift, so that is basically Vi cos theta. So what is V? V is the voltage drop across that element. Here it is Vz, and we have calculated this V already. I, the current through that branch, that we also know, that is basically I1. Okay, and the next thing is that this is the power factor, that is the angle between this Vz and I1. That is another thing. So for this we need this theta. For that we'll need to go for this phasor. So how the phasor will be looking like? So this is a pure resistance. Uh, this is R. Okay. So we have so this A2 is going here, A3 is coming from here. So we can do one thing that uh, see. So this is basically I1 is equals to I2, or we can say I3 equals to I1 plus I2 phasor. So this is I3, that is the resultant of I1 and I2, and I will say I2 is this, that is 3.25 amperes. Why? Because this is a resistor and we are taking this as reference, so this will be in reference. So we are taking I2 as reference, and in this phasor itself, in this direction only, there will be this voltage drop V, because V is what? V is I2 into R. So R is having 0 degree phase shift. So that's why the voltage drop across this branch, that is VE, will be in the same phase like this. Okay. So this is I2, this is I3, and the next part is this is I1. So the resultant of I1 and I2 will give us I3. Okay, this thing is clear, and we can see from this also. Now the question is to find cos theta. So we know that the resultant is what? So okay, so it is 8.25 equals to under root of 3.25 square plus. So this is basically simple vector solution, plus 2 into 3.25 into 5.75 into cos theta. So I think you have, if you have seen the live session, so I have like used this formula many of time. So it is like just to calculate this cos theta, you can solve this, and so from this you can get this theta. That will be some value. I'm not calculating this thing, but this is the thing. So theta you will get cos theta basically. So theta will be cos inverse of that value. You will get theta also, but we only need that cos theta. So the power factor we just calculated. This is done from this formula. Okay, and the power consumed will be what? This is the formula. So we know Vz, we know I1, and we know cos theta. So we can get the power also. Okay. So whenever if you get some elements apart from resistor, either capacitor or inductor, then you should keep in mind the angle between the voltage and the current of that element. Only then you should consider what will be the power being used by that element. So keep that thing in mind. So this was about this, and then we have a typical bridge circuit. So again, if we so this they have to we have to find the D factor and Q factor. So based on that table which I have told you, so they are telling to find the D factor of the C4R4 and Q factor of L2R2. So using that table, you should know what will be the D factor and Q factor of these two coils. That is basically the I will say first part. Okay, first thing. The second thing will be balancing this circuit. So it will be R2 plus omega L2 J equal to R4 minus J by omega C4 divided by R3. So now if you will start directly solving from this part, then you will be in difficult situation, because then this will become complex. So instead of that, either solving by this, you just rearrange some things. R4 minus J omega C4, this will be R2 plus omega L2J. So once you solve this, so it is easy to like solve in this configuration. So you will get some real part and imaginary part, and this there here it is only just the real part of the R1, R3. So you can equate them easily and you can get to your solution. Okay. So that is the second part of this question. So first part, you should know what is the Q and B factor. Just look for the table. You will get that, and then carefully balance the equations. That is another thing. Now the next question. So again, there will be CT and PT based questions also. So this is a current transformer question. So this is talking about, so there is a like 1000 ampere going from this main supply. So we have this CT here, and we have used an emitter PMC, basically an emitter here, which is taking 10 amperes, which can take 10 amperes max. So we have this turn ratio 10 is to 1000. Okay, because it is given an AC current that can go up to 1000 ampere, that is this one. We have an emitter of range 0 to 10 amperes and internal resistance. So this is having internal resistance 10 ohm to measure this in that CT. We will use a suitable CT to change the range of our emitter. Assume the CT to be an ideal transformer. So the first part is estimate the power that will be consumed by our CT and emitter arrangement while measuring 1000 ampere current. So these type of questions, this is from assignment only. So if you have to calculate the power, so that is easy. Yeah, so the power from in CT, because CT is not having any of its own resistance. It is an ideal transformer, so that's why PCT will be. We know the current I square into R. So this is I square R. So this is secondary current. I will say this is equals to IS, secondary current of the CT. So we'll get 1000 watt. That is the power being dissipated in this emitter, 1000 watt, or in total this CT and emitter arrangement, which they have to. Now the next question, estimate the equivalent resistance of a CT and emitter arrangement. So based on primary, so I think these machines, you have been told, or in this lecture also, you have, in this course also you have been told about this. Like if you have to convert something from primary to second, like from secondary to primary, then it is like either you can like. So the basic is like to go with this thing, like using that turns ratio, and by using that you can calculate that what will be the equivalent resistance on the primary side of this. So it will be equal to our primary 10 ohm is the resistance, then we have this uh, turns ratio 10 by 1000 square. So it is basically 10 into n2, sorry, I2 by I1 square, and this was, I will write it here, I primary, R primary equals to R secondary into I2 current full scale divided by I1 का square, or R secondary into N1 by N2 का square. So this thing. If it is other way around, like if you have to calculate for this primary for secondary equivalent, then this will reverse. Okay, that is the thing. So this is also fine. Then again, I told you like operation amplifier questions can also come. So this is like one of the assignment questions. So you have to calculate V naught here. I told you first to check whether that is a negative feedback, a comparator, or a positive feedback system. So now we have seen that this is a negative feedback system. If it is so, then you can use that virtual short concept. So this is 0 volt. That 0 volt can come here, and now you have to use either nodal or whatever you find suitable. You can use that electrical electrical technique. So I use nodal. So this will be, let's say, I1, I2, I3, and just also keep in mind no current will flow inside the op amps, so that makes things much more easier. So this will be 0 minus 1 divided by 4k plus 0 minus 3 by 4k equals to 0 minus v naught by 2k plus equals to 0. Okay. So if you solve this, you will get v naught from this question. That is simple. So just like for op amp based questions, just see in which feedback that op amp is being uh, being operated. Okay. Now the next question, that is for dual slope. I told you like the basic equation for this dual slope is like so they have given this integration time 2000 clock cycles. They have given this de-integration time 190 clock cycles, and they have this reference voltage 4 volts. So yeah, estimate the value of the input voltage. So if you know the basic that equation, so this is V reference into TD. If you know this, you can solve. So V reference, you know, 4 volts. TD, you know, 190 clock cycle. V in you have to calculate, and TI also you know. So you can get V in easily. So now they are asking the next question, the resolution. So resolution questions also is they are important. So resolution is basically the minimum value of voltage being measured. Okay. So they were yeah. So that is minimum value of voltage being measured. So now so V in first for the first part. So this is first part of the question. So first part, this is second part of the question. So this V in will be V reference is how much? 4 into TD is 190 divided by 2000. So we will get V in here. V in from this part. Now the resolution will be uh, see we have this so maximum voltage which this dual slope can measure is still that reference voltage that we know. It cannot go beyond that. So it is this voltage 4, and this is the like the clock cycles, like number of this number of like clock cycles for integration time which is being taken here. So this is 2000. So basically what I am doing, uh, I will say, so there was some input voltage in the first part. There was some input voltage. Okay, it took 190 clock cycle for this measurement. But if what so resolution is what is being measured in only one clock cycle. Okay, so instead of 190, here it is like, so reference we have this 4 divided by the this integration time into one clock cycle. So basically, this is for like understanding. Like 190 clock cycle it took for that V in input voltage to get to measure that. Okay, but how much voltage it will be measuring in one clock cycle? So we have this reference voltage, we have this integration time in one clock cycle. How much it will take? So this is like the resolution of this dual slope. Okay, so this has been told to you in lectures also. So this will be in millivolts. It will come. So you can solve this. I think it will be two volts, 2 millivolts. Okay. So this will be the formula for dual slope, that main formula, reference formula, and then this resolution concept. You should know that thing also. So another ADC based questions also can come. So just prepare for that also. So another like typical questions are like where you have these diode type of structures which gives like full wave rectifier for outputs. So I will not solve, but because these solutions you already have, but like give you the the idea of this, like V in is here. So this was like this sinusoidal signal. Okay, the output, what output we will get, since this is a 4 diode structure. So we will get an output of like this, a full wave rectifier circuit, a full wave rectifier signal output. This was input. Now the first question is the RMS value of the input voltage V in will be what? So we know that PMMC measures average value and deflect. So whatever the in question, whatever value they give for this full scale deflection of PMMC meter, that is the average value. This is very important to keep in, this thing you should keep in mind. So the average current value they give for like full scale deflection of this PMC meter, every time it will be average if this that is the case of PMC meter. So if this is average, you have to find the RMS value of input voltage. So since there is an op amp, you will first check that this is negative or positive. So this is a negative call. This is negative feedback op amp. If that is the case, then this is the I input. Okay, and this same I input is being traveling through this PMMC. So I input is equal to the I PMMC meter current. This thing you have to keep in mind. Then V in divided by I in will be what, 25 kilo, because by virtual short this is 0 volts. Okay, so this is 0 volts, then this we have 25 kilo ohms. So it will be what, V in equals to 25 kilo into I in. But this I in is what, average value, and we need this RMS. V in RMS will be what, it will be 25k into I in RMS. Okay, so because RMS only we can relate, but this is average, this 2 milliampere is average. Now we will take use of these things and the table which I have given you in the week 2 or week 3 of this live session. So for a sinusoidal wave, the full wave rectifier signal is like this. So I average is equals to what, 2 Im by pi. If you know the table, you will know this formula. Otherwise, you can derive also. But yeah. So from this, we can get this peak value of this output signal or output current Im. So that will be I average into pi divided by 2 equals to Im. From here, we can get the RMS value of this signal. That will be I RMS will be equal to Im by root 2. That is also from the that is the RMS value of a sinusoidal signal. So that will be I average into pi by 2 root 2. Now we can use this in this, because now we have this RMS value of the current. So the RMS of input will be what, 25 kilo into Im, the peak value of that. Sorry, I average into pi by 2 root 2. And what was I average? 2 milliampere. Okay. So you have to be careful. 2 milli. So you have to be careful about, like, first thing, what has been asked. So they have asked like RMS value of the voltage, input voltage. Second thing, what is being measured. So here the average value is being measured. Third thing, how to convert that, whatever is being measured, like here it is average value, how to convert that back to like whatever has been asked to us, that is into RMS value. So all these things you have to keep in mind in order to correctly answer these kind of questions. So these can be tricky, but if you know the concept, if you know what that particular ammeter or voltmeter is being reading, then you can easily solve that. So instead of PMMC, it was being like some electrodynamic or moving iron kind of meter. Then it's being indirectly said that that is an RMS value of the current. Then you don't have to convert these kind. Then you don't have to do these kind of conversions. But since this was an average value of current, that's why you have to convert that into back to what, RMS value of the current in order to get the RMS input. Now the next question, estimate the RMS value of the input voltage V in the meter if the meter shows 50 meter deflection. So 50 meter means 50% of average current. So you just have to multiply like here 0.5. You will get the answer. Okay. But if this was the case for MI meter, then that will be zero point 0.5 square, because there is like it is I square now something. Okay, don't mix both of that. Leave that. So yeah, just focus on this. So for this, like for 0.5 50% deflection, you have to multiply this with zero point 0.5, the current, the average current, that will reduce by zero point 0.5 factor. Okay. So again, that estimate the input resistance. So for input resistance, the thing is that we should know these basic things. I'm saying in Z input, it can be R I in. So V in is whatever the input current is. I in is whatever. Sorry, V in is whatever the input voltage. So V in we know. We have just calculated V in RMS. Now one thing also, like if you are using V in RMS in numerator, then this should also be what in RMS. If you are using this in average, then this will be also average. So just keep in mind to keep these things in the same like either that should be RMS or that should be average. Then you will get RN. Don't do like V input will is in RMS and I in is in average. Then you are dividing them and you are getting the R input. That will be wrong. Okay. But either it is RMS or average, both the quantities, it does not matter. You will get R input. Okay. That is one thing. Yeah. So I thought these questions might be like it will give you an overall view of whatever you have been taught in this course, in this lecture. So this was about this session. I hope you learned a lot from this course, and you will uh, you will do good in your exams. Like just go through the live sessions, go through the lectures, go through the assignment questions. Questions are very important. Uh, Keep in mind the tables which I have told you, and I think that will be enough to do well in the exams. Otherwise, like I hope you learned quite a lot about this electrical measurements and electronic instruments course, and how there are these electronic instruments are being used. What are the things to keep in mind while measuring them? Different kind of circuits, all those things. So yeah, so that's all from my side. If you have any doubts, you can tell me. Or I think before exams, you still have the discussion forum live. Like sorry, not live. It is still active. So if you before exams you get any doubts, if you need any clarification, you can ask whenever you want on that discussion forum. So we will love to share that or like give you the solutions for your doubts and all those. So yeah. So thank you for listening and thank you for being part of this course. Yeah, if you have any doubts, you can ask me. Otherwise, yeah, you can leave. Yes, yes, you can open the mic. Switch on the mic and you can ask.
Sir, please explain hysteresis band problem.
Okay, okay, okay. History is important. Okay. I thought I have one question based on that. Okay, I will give that question later. I'm just looking for that question. Just wait. Yeah, got it, got it. Yes, yes, yes. So this is a simple question. So let's say we have to find the stresses band of this thing. Okay. So first of all, you should know why, because this is a positive feedback. Okay, that one thing. Then we will solve the equation. So we will see at this point how much fraction of this voltage is being seen at this point. Okay, so that will be so we have 5 volt. We have to compare whatever we are getting from this 5 volt thing. So this will be uh, I'll say, let's say this is V plus, this is V minus. So what will be V plus? I'm simply using this plus V plus. So I'm simply uh, getting this expression of V plus in terms of V output and V input. Okay, at this part. So this will be 8k equals to 0. So this from this we will get uh, V plus by 1 by 2k plus 1 by 8k equals to V naught by 8k. So this will be V naught by 8k plus V in by 2k. Now if we solve this, this will be plus 10, yeah, 10k, and we have 5k. So basically this will be 4V in plus V naught by 5 equal to V plus. So this will be like, after solving this we get, so the in like the concept is like we have to find an expression of the non-inverting side terminal voltage that we just got. So that will be in terms of V input. So irrespective of whatever there is at this side and at the negative feedback and a positive feedback, whatever there it is, like whatever elements, we have to just find the expression of V plus. So we got this expression V in V naught. Now, in order to get the limits, we will do that V plus if it is greater than 5 volts. So now what is the comparison voltage for this V plus? So basically split triggers are acting like a comparator now. So this V plus, if it is greater than V minus, and V minus is what? That is 5 volts. So that's why I said 5 volts here. Okay. Or I can say V minus. If that is greater than, then we will get V naught as what? Then V naught will be plus V saturation. Fine. So that means we can replace this by V saturation. So it will be 4 in by 5 plus V saturation greater than 5. Now if you solve this thing, you will get V in greater than 25 minus V saturation by 4. This is one equation. Another case will be when 4V in plus V naught by 5 is less than 5. That will happen when V negative is when this then if this happens, then means V naught is what? Minus V saturation, because our this is non-inverting side terminal voltage, sorry, inverting side terminal voltage, and that is greater than the non-inverting side terminal voltage of the op amp. So that will do this, like that will make this as minus V saturation, and if we put that here minus 15, sorry, minus V saturation divided by 5 less than 5, so we will get V in less than 25 plus V saturation by 4. Okay, let me add another page. So we have two equations. We have one is 25 minus V saturation by 4. One is V in less than 25 plus V saturation by 4. Here it is 4. So what does these limits signifies? This signifies when V in will become greater than this, then V naught will be plus V saturation. When V in will become less than this, it will be then V naught will be minus V saturation. Is it? Yes. That's what we have been told. So if we put this here, then it will be 25 plus V saturation is what? I think in question it was given 12. In question it was given this 12 supply was there. 12 here minus 12 here. Okay. So this was 12 minus 12. So that means 12, 25 by 12 by 4, that is V in, and in this it will be V in greater than 25 minus 12 by 4. So we will get 10, 13 by 4, 13, yes, 8 plus 5, yes, 13 by 4. So, and this is V in less than 25, 35, 37 by 4. So we have these two limits. One is this limit, another one is this limit. So let's say we had this V input like this. So this is 37 by 4. This is 13 by 4. So you can say that this is the upper threshold limit and this is the lower threshold limit. In short, we are saying that if the voltage goes if the voltage goes less than this or above this threshold limit, then we will be seeing some changes. Like V naught will become plus V saturation if V in becomes greater than what, 13 by 4, this lower threshold limit, and we will see V naught equals to minus V saturation if V in become less than 37 by 4. So these we have these two limits. So in this way you find UTP and LTP, that is the upper threshold limit, upper threshold point, and lower threshold point. And what is hysteresis band? It is basically the difference of these two, UTP minus LTP. So it will be 37 by 4 minus 13 by 4. So this will be hysteresis band. So band is basically, hysteresis band is basically in which the transition is happening. So hysteresis band. So for important factor for hysteresis band is like to calculate properly this UTP and LTP. And the important factor to calculate UTP and LTP is that to correctly compare the non-inverting terminal voltage and the inverting terminal voltage, as I did here. Okay, so don't get scared by seeing, okay, this is simple, this is one question, but if you get any bigger negative feedback or positive feedback elements in that, because let's say you have some parallel capacitance or some resistors here, or like some voltage sources here, something like that, don't don't be scared for, don't be scared by that. Why? Because you just have to get the expression for this non-inverting side terminal voltage, and if you know this inverting side terminal voltage also, you just have to compare them and get two comparable equations, and based on that you calculate this like what changes will be happening at the output, whether it will be plus V saturation or it will be negative V saturation. Based on that you get two limits, and accordingly either putting minus V saturation or plus V saturation you get UTP and LTP, and using UTP and LTP you get the hysteresis band. Okay, so that was about hysteresis band. I hope this the doubt is clear.
Yes, sir. Thank you, sir.
Okay, yeah, welcome. So if so do you have any other doubts or anything?
No, sir.
Okay, thank you. So if others also, if they don't have any doubts, so we may end this session here. And yeah. Okay, so if you don't have any doubts, so anyway, I am available. Even sir are also available in that discussion forum. So feel free to ask any doubt, any type of doubt in that discussion forum before exams. We will clarify that. And thank you for this, and thank you for part of this session. Okay, then I will be ending the call. Okay, thank you.